We can use the She to measure the potential of other kinds of electrodes. For example, let us consider one electrochemical cell with a copper electrodes and a She. In this case, the copper electrodes is the cathode and the She is the anode. We deduce the effect from the increasing in mass of copper electrodes from the operation of the cell, which is consistent with the reduction reaction. At the anode, the hydrogen gas is bubbled into a hydrochloric acid solution. The platinum electrodes provides the surface on which the oxidation takes place. Hence, the hydrogen gas is oxidized into H+ ions and release 2 electrons. The H+ ions enter the HCl solution. The electrons move from the platinum electrode to copper electrode through the external wire. The voltmeter displays the value of standard cell potential, which is positive 0.34 volt. At the cathode, the copper 2+ ions from the copper sulfate solution reduced to copper solid and deposited on the copper electrode. As the result, the mass of copper electrode increases. As the reaction proceeds, the anode half cell is rich with positive ions, whereas the cathode half cell is excess in negative ions. To maintain the neutrality, the chloride ions from the salt bridge migrate to the anode, while sodium ions from the salt bridge move to the cathode. We can write the half cell reaction as follows. We can calculate the standard reduction potential of copper by using the formula of E naught cell is equals to E naught oxidation plus E naught reduction. From the calculation, the standard reduction potential of copper is positive 0.34 volts. Another usable equation for determining E naught cell is given as E naught cell is equals to E naught cathode minus E naught anode, where both E naught cathode and E naught anode denote the standard reduction potential respectively. The standard electrode potential of zinc can be obtained in a similar fashion by using a cell with zinc electrode and a She. In this case, the zinc electrode is the anode because its mass decreases in the operation of the cell as it's consistent with the oxidation reaction. At the anode, zinc electrode is oxidized to zinc 2+ ions and release 2 electrons. The electrons produced at the zinc electrode move through the external wire to the platinum electrode of She. The voltmeter displays the value of standard cell potential, which is positive 0.76 volts. At the cathode, H+ ions from the HCl solution is reduced to hydrogen gas by gaining 2 electrons. As the result, we can see bubbles of gas released at the cathode, which is the hydrogen gas. As the reaction proceeds, the anode half cell is rich with positive ions, whereas the cathode half cell is excess in negative ions. To maintain the neutrality, the chloride ions from the salt bridge migrate to the anode, while sodium ions from the salt bridge move to the cathode. We can write the half cell reaction as follows. The standard reduction potential of zinc can be calculated by using the formula of E naught cell is equals to E naught oxidation plus E naught reduction. From the calculation, the standard oxidation potential of zinc is positive 0.76 volts. We can evaluate the standard reduction potential of zinc by reversing the oxidation reaction. Remember that whenever a half cell is reversed, the E naught sign also changes.